Hello and welcome on board. This is Design the Engineering Process, a channel where we give walkthrough on process engineering operations and design. Let's dive in. Intermediate, we have a design mission in hand. Your mission, should you choose to accept it, simulate the production of hydrogen gas through steam methane reforming. Our feed composition goes as follows. We're going to be working with the mole fraction, 100% methane, representing our natural gas. Now, ideally for the natural gas, we predominantly have methane in our natural gas, and not completely methane, predominantly methane, and some traces. In some cases, we do have traces of other hydrocarbons and components, such as ethane, propane, and other components. But for the smoothness, for things to go very smooth with respect to our simulation, we're just going to be using methane, and then we're going to be having steam of 100. We're going to be having steam 100% also for our feed, with respect to the mole fraction. For the feed conditions, our steam is going to be at 3 bar 250 Celsius. Our methane is going to be at 1 bar 30 Celsius, with a flow rate of the methane specifically having a flow rate of 50 kilogram mole per hour and a steam to carbon ratio of 3 to 1. Process setup for our steam methane reforming reactor. The setup goes as follows. Reactor inlet temperature target is 800 Celsius. Reactor pressure 15 bar. Steam to carbon ratio 3 to 1, which is still 3.0. Then methane conversion 85%. We're expected to convert 85% of our methane for the SMR reaction, and we're expecting a pressure drop of 1 bar inside our reactor. The reaction goes as follows. We're having our methane reacting with water to produce carbon monoxide and hydrogen gas. The stoichiometric coefficient of our SMR reaction is also given. Then our product yield targets for our hydrogen, the outlet of our reactor, expecting a purity of 90% respect to mole fraction for our hydrogen. And then the hydrogen production target, we're expecting about 120 kilogram mole per hour of hydrogen respect to the flow rates. So with this, we have most of the information needed to carry out our simulation. Only missing gap, if you were able to notice, was that we were not given a flow rate for our steam, but that's where the steam to carbon ratio comes in play. We have a ratio of 3 to 1 respect to steam to carbon. So if our carbon, which is our hydrocarbon, our methane gas is 50 kilogram mole, that means our steam is 3 times more than our methane. So we're just simply going to multiply 50 by 3 to give us 150 kilogram mole per hour as the flow rate for our steam. With that, we are good to go. So let's head to the simulation and modeling environment. We're currently in the modeling and simulation environment. And as always, for those of you who are new here and are confused how we got here, you're probably in the right dimension at the wrong time. So you need to check out our previous content to know how to get here. For those of you who are at the right dimension at the right time, we're going to be using a food package that we have always been using, the very versatile Mr. Peng Robinson. So Peng Robinson hydrocarbons go hand in hand, very versatile. So firstly, as always, we drop our stream, our feed stream. Remember, we're having two feeds, our steam and our natural gas. So we're going to be dropping two streams. We're going to call this our natural gas, or we could just call it methane. You already know it's natural gas. So methane, remember, at a temperature of 30 Celsius, 1 bar. And I'm just going to change this to the Euro SI units because of my units. I'm more conversant with this setup, having these units. Yeah, so I think you're good to go. And for the methane, remember, it was 50 kilogram mole per hour respect to the molar flow it was given. And then for the composition, you can see we have selected 4 components. But this is a stream 100% made up of methane, so it's just going to be one. With respect to mole fractions, we're using mole fractions today. That's what we're working with. So 100%, and we have successfully created our stream, 100% gas. Right, and respect to mass flow rate is around 802.1. So next up, our steam. We're going to call the steam. We're going to give it a temperature of 25 Celsius. Was at 3 bar with respect to the information provided. Mole fraction, remember we said it's going to be, it's the steam to carbon ratio is 3 to 1. So it's going to be 50, it's going to be 3 times more than the flow rate of our carbon. So 50 times 3 is 150, so 150 kilogram mole per hour. Then we're going to specify our composition, which is 100% water in the stream. So this was going to be 1. Okay, you can see it's completely liquid. So we have successfully, no, not really successfully, it's steam 250 rather, not 25. So it's in the gaseous phase. We've successfully created our streams. So before we go into the reactor, we are expected to carry out mixing, because the whole essence of the steam methane reform SMR reaction is, it's going to be, it's a reaction made up of water and methane to generate hydrogen gas, and the product is hydrogen gas and carbon monoxide. So we need to mix them, and to do that, we're just going to drop a mixer. This is 3 bar, 1 bar. We could just mix it. Just simple. So let's go. Methane, steam. We're going to call this. We just call this mix. No, we just call this mix. So, all right. So zoom out to have more space. Next up, part of our parameters given with respect to the SMR setup is that we need to have an inlet condition of 800 Celsius and a pressure of 15 bar. Wow, a pressure of 15 bar respect for the reaction. If that's the case, then we need to do some major pressure increment. But the downside to this is that methane is, let's check the mix first of all. Oh well, we're lucky. It's still completely gas. So that means we could just use a compressor. After mixing, we could just simply use a compressor to raise our pressure 20 at 1 bar, raise our pressure to 15 bar, and hopefully that might properly raise our temperature. So compressor, we're going to plug in our mix. It's a compressor, we need to specify an energy label. So it's just call this com1. Call this compressed mix. And then let's specify a pressure change from here. Change in pressure of around 14 bar. Alright. Since you're currently at 15 bar and we're at a temperature of 629.6, so we just have to do some extra heating to take us up to 800 Celsius, so we can go on with the reaction. So we're going to drop a heater, but rather than dropping a heater, let's do something different today. Let's use a heat exchanger. We're going to bear in mind some optimization concepts for this work. Let's use a heat exchanger, and we're going to send in our compressed mix through our tube inlet, and we're going to call this we could call this tube out. And for now, the shell side, we don't have anything inside going through the shell side. So for now, we're just going to leave it blank. I know we have a red message. It requires a product, okay, requires a feed stream that's with respect to the shell side. So now we could just, I think we could just let that be. Then it's still, the stream is empty because it's still sky blue. It has to be dark blue to have a variable assigned to it. So let's go to our worksheet, and we're just going to specify pressure drop. Let's specify a pressure drop of 0.5 bar. I think that should do, and raise this temperature to 800 Celsius. Good. We've assigned a variable, so it's dark stream. It's a dark stream, but the equipment is not successfully functional because it lacks a value for the shell side of the heat exchanger, the shell inlets and outlets. But we're going to work on that. We're going to work on that very soon. So since we're incurring a pressure drop in our heat exchanger of 0.5 bar, we might as well just increase our pressure to 15.5 bar to cover the 0.5 loss. Design parameters and change in pressure. We're going to make this 14.5 bar. Good. That way we are currently on 15.5 and we use 0.5 to our heat exchanger. And next up, you can see that we are ready to go inside our reactor. 800 and no, 0.5, my bad. It's supposed to be 15. We lost 0.5 bar. So we are ready to go into our reactor. So we haven't used we have never used the reactor prior to all the contents that we have been carrying out all this while. So this is the first time using the reactor, and the reactor, let's just type in reactor here so we can see all the reactors we have. These are the reactors we have: the continuous flow stirred tank reactor, CFSTR in short form, plug flow reactor, the conversion reactor, equilibrium, Gibbs reactor, and yield shift reactor. For simplicity of this content, we're going to be using the conversion reactor because we already have a conversion rate. That was the methane that was given to us. So we're going to be using the conversion reactor. And conversion reactor, before we use a reactor in Aspen Hysys, before we use a reactor in Aspen Hysys, there is something very, very important we need to do. Otherwise, it's going to be used as basically the whole operation. The reactor operates based on the reactions being carried out. Now we're already given a reaction prior to our previous content. If you can remember, for the electrolyzer, we did not specify any reaction. We already had the inbuilt reaction because of the electrolyte wizard that we had. So the electrolyte wizard generated the electrolysis reaction. But here we do not have an electrolyte wizard because we are working with the normal Aspen Hysys properties. We're working with the normal Hysys properties, not the Aspen properties. So we need to specify a reaction. In summary, that's all I need to say. We need to specify a reaction, and to specify a reaction in Aspen Hysys, we go back to our properties. Remember, we have component list for selecting components, fluid package for selecting a fluid package, which is Spring Robinson in our case, and then reactions. That's the fourth tab, the fourth option. This is where you specify reactions that you use inside reactors. Without specifying a reaction set, the reactor cannot carry out any reaction. It's just going to basically be a simple tank where you send in an inlet and you receive your outlet. At the outlet, you receive your whatever you sent in through the inlet going out through the outlets without changing anything. So it's just going to be passing like It's just going to pass without any reaction. So you do need to specify a reaction for you to have changes. And to specify a reaction, you click on the add reaction and set the reaction type. Well, add reaction firstly. Let's add our reaction firstly. We're going to be working with the Hysys as reactant source, Hysys, because we are working with Hysys component. We're working with Hysys component for the composition and the food package. So we're working with the Hysys also, respect to the reaction sets. So types of reaction we have the conversion, equilibrium, heterogeneous, catalytic, and kinetic and simple rates. We're going to be working with the conversion reactor. So let's use the conversion reaction. We have the reaction, and then add a fluid package to it. So we're going to be adding Peng Robinson. We're attaching that. And next up, we could just double click on this and select the component. Mind you, you could just name this active reaction. You could name this. We could call this SMR reaction. Name that for easy reference. Then we double click to go inside, and then we add our components that undergo in the reaction. Remember, we're having methane, H2O, and then for the products, we're having hydrogen and carbon monoxide. That's the reason why we added hydrogen and carbon monoxide to our components. So a base component is the component that you use to measure the progress and the rates of your reaction. Basically, for our case, it's going to be methane. So we're going to specify methane base component. We're going to specify methane as it's not popular. I think we're supposed to have methane somewhere. So let's specify our stoichiometric coefficient firstly. For the stoichiometric coefficient, we're having 1, 1, -1, -3, and it stems from our reaction. The stoichiometry stems from our given reaction. So we're having 1 and 1 on the left hand side, and for the right hand side, we're having -1 and -3 to balance up the whole reaction. So back to our reaction, specifying our reaction. For the stoichiometric coefficient, we're having 1, +1 for our methane, having +1, hydrogen is -3, and for the carbon monoxide, well, carbon monoxide is 1, I believe, -1, and good enough. So balance error. This is very important. The balance error tells you if your stoichiometric balance is correct or not. What I mean by this, for example, now if the stoichiometric coefficient for the given reaction was not correct, we would be having an error giving us a value of error value, telling us basically that the stoichiometric coefficient for this reaction is not correct, and that gives us inconsistencies in our reaction. So let's change this. For example, let's say this was 3. You can see we have an error, 32, error by 32.08. If I change this back to 1, it's completely 0. So you need to bear in mind that your balance error needs to be 0 for a very good reaction, for everything to accurately go on. Then after specifying the stoichiometric coefficient, we can select our base component, and our base component is supposed to be methane. So where we got the error was with respect to the sign convention. We're going to turn this the other way around, -1, -1, +3, and +1. But that way we can have methane as our base component, which we do. And then we're missing something, which is our overall reaction phase. Well, let's just leave that as overall. The C0 specifies, the C0 represents our conversion rate, which we need to specify. Remember the conversion rate of 85% given for methane. So let's push this to 85%. And that way we are good to go. 85%, and we're ready after specifying the C0. Remember, represents your reaction rate. With this, you can see that we have successfully created a reaction set for our SMR reaction, and we have a green message at the top for us, ready and independent. So let's head back to the simulation environment. So plugging in our reactor inlet, which is our tube out. We're going to call this the vapor. Our top bottom would be called liquid. And then we go on ahead to our parameters to specify our pressure drop, which is 1 bar. 1 bar. And then we head on to the reactions tab. We select our reaction sets that we created earlier, and it pops up our SMR reaction. You can see the components specified together with the stoichiometric coefficients specified for the conversion. It's 5% specified. Let's have a look at our products. But before that, take note of the flow going inside the reactor. A total of 200 kilogram mole per hour with respect to the molar flow rate. And at our vapor outlet, we have 209.1, which is greater than the inlet. And at the bottom, we have 75.94. That's a total of 280 plus kilogram mole per hour molar flow rate, which is greater than the inlet. And the reason for this is that we are looking at the molar flow rate. And with respect to the molar flow rate in a chemical reaction, the number of moles could increase or reduce. And in our SMR reaction, as we have it, there was an increase because of the products new products that we formed due to the reaction, the hydrogen gas and the carbon monoxide. So the increment, if you see a variation in your flow, respect to what went in not being equal to what came out, it's not much of a problem. Respect to this particular simulation because it's just a chemical phenomena. So let's go on ahead, just check our hydrogen gas. We have 61%, approximately 61% of hydrogen gas produced, and 20.3% carbon monoxide. We have 15% unreacted water and 3.5, approximately 3.6% unreacted methane gas. So let's check the bottom. We have 99.99%, approximately 100% water at the bottom. So a little bit short on our purity, respect to our purity, but this we haven't carried out the separation yet. So let's try separating the other components from our vapor, the other components from our hydrogen gas. Let's try doing that, even though it might be a bit hard. But at the very least, we could separate water. Carbon monoxide, hydrogen gas, and methane might be problematic. As such, we might need to conduct some other processes such as cryogenic distillation, which we have already covered in our previous content. So we might just stop at the separation of water. We have already produced our hydrogen gas. So we might try separating water and see if we can hit that benchmark of around 90% or greater purity for hydrogen gas after separation. But before that, our heat exchanger. So with respect to the optimization, what we have for temperature is 120.4 Celsius. We were supposed to plug this into a heat exchanger, basically recycling heat energy to avoid wastage. But unfortunately, it's going to be impossible because the temperature after the reaction comes out lower than the inlet stream. So we do not have any heat to give the stream because the temperature here is lower. As such, if anything else, the opposite of what we need might happen. The heat from the stream would be sent down here. So that's not what we desire. Fortunately, our optimization concepts would not work here. So we're just going to go on ahead and replace the heat exchanger with a heater. But you do get the concepts. Unfortunately, it wasn't possible. So I'm just going to plug this in compressed. This as our tube out and call this our E heater because it's a heater requires an energy stream heater. And then put this button active. And yes, we are good to go. So Fix this up. So with respect to the separation, we're just going to carry out some condensation and knockouts. And for that, we're going to be using an air cooler and a knockout drum, where we use our air cooler to condense our gases into liquids to form some liquids, and then we use a knockout drum to separate the gas from the liquid. We haven't used an air cooler also in all our previous contents. So an air cooler, you just search that. Good. Air cooler. This is what it looks like. So click process stream inlets. Plug in our vapor that's all going to condense. The process outlets, we need to label that. So we're going to call this cooled, cooled vapor. Right. Then we head to the parameters tab and see temperature, outlet temperature. We can specify the outlet temperature. We are currently at a temperature of about, we are currently at a temperature of 100, right, 120 Celsius. So we can just drop that temperature to 30 Celsius, I believe. Just put it. Remember, the air cooler is an equipment that cools a particular substance or an object down to ambient temperature. It doesn't cool it below ambient temperature. Ambient temperature is like your environmental temperature, typically around 25 Celsius, 25, 30 Celsius. Well, it does depend also. It also depends on the region. But the air intake, what we have here, preset is 25 Celsius for the air intake. That's the ambient temperature. So we could just make ours slightly above the outlet temperature of our stream. We just make it, let's say, 35 Celsius. Good. And then we specify our change in pressure. We could just give it, let's give it 1 bar. Temperature cross, it doesn't work. So let's give it 40. Not good enough. Give it 50. Still not good enough. Let's give it 100. Still not solved. You know what? Let's head to the worksheet and specify this. Let's give it 50 Celsius here. Alright, that worked. Let's give it 20. Temperature cross. 30. That works. So let's put it on 35. That's good enough. Good. So next up, we're going to drop a knockout drum, and our separator is what is used as a knockout drum. All we have to do is just change the icon. A knockout drum in our case, we just change the icon to look a little bit different. Maybe we could use this. It's not much of a defense bar, so good enough. So go in, again, wood vapor, and we can call this gas 2, call this liquid 2, and let's have a look. Alright, so at the bottom we have 30.75 kilogram per hour, and we predominantly have water, 100% water. For the tops, we have 178.3 kilogram per hour, and we have a hydrogen purity of 71.5%. So we are a little bit short on our purity benchmark, unfortunately. For us to improve the purity, we might need to carry out further processes of things such as maybe carry out water gas shift reaction to improve our hydrogen yield and use up more of our water, and then carry out a pressure swing absorption or cryogenic distillation, which would go a little bit out of context and scope for this particular content. But with this, we do have the basics for the SMR reaction. We do have the basis for the SMR reaction and how it's carried out on Aspen Hysys. So we could just check the flow with respect to the quantity to know how much we have. We're expected to have 120 kilogram mole power of hydrogen. So to check the quantity with respect to the molar flow users, we just multiply our mole fractions by our mass fractions by our molar flow rates, and our molar flow rate is 178.3 times 0.7150, and that gives us 127.485. That's slightly above our benchmark, so we have successfully attained that benchmark needed for the respect to the quantity of a hydrogen gas. The only problem with respect to the design task is that we were not able to achieve the 90% and above hydrogen gas purity in our outlet stream after separation. To do that, we might need to employ further extensive processes, which we would probably not be doing. We did cover one of the processes, which is cryogenic distillation, in our previous content. You can use that to improve the hydrogen gas purity and separate the other components in the together with the hydrogen gas, which is our methane and carbon monoxide. So with this, I believe we can say we have almost successfully carried out our simulation for the SMR. We do have the basics, the fundamentals, the whole idea behind it. And if you followed us down thus far, as always, please make sure to like, subscribe, and click on the notification icon. Thank you.